Okay, I've set up an example, and the center of this example is a collision, but it has a little bit of a multi-part aspect to it. So consider building two pendulums. Each of them is 0.3 meters long, and the first one, the red one, is a 100-gram steel sphere, and the second one, the blue one, is a 200-gram steel sphere. And I'm going to pull the red one up to the side so that it gets elevated to a height of 0.1 meters above the bottom of the swing, and it's released from rest. So it's going to go down and it's going to bounce off the other one in an elastic collision. And I want to know how high each sphere rises afterwards. So we only really have two types of processes to deal with. We have to do a conservation of energy with gravity, and we're doing that for the downward swing of the 100-gram pendulum, and then we're doing it for the upward swing of each of them. So we kind of have to do that one multiple times. And the second process is an elastic collision. And I will do a demonstration of the relative to center of mass method of calculating an elastic collision. And hopefully we'll see that the energy of the elastic collision is conserved because it's supposed to be. And you'll see that this method is actually fairly straightforward when we get to it. So let's start calculating. So first, this should probably be red because it is the downward swing of the 100-gram ball. And in that, we have mgy is equal to 1/2 mv squared. The initial energy, there's no work going on, so I don't have to add work, is equal to the final energy. And notice that the m's cancel, so might as well just cancel that. And we end up with 9.8 times the height is 0.1 is equal to, let's move the 2 over there, is equal to v squared. So that tells us that v is the square root of that. Let me get myself a little scratch sheet over here so I can do calculations. So h is 0.1 and v is square root of 2 times g, which is 9.8, times h, which is that thing, and I get a v of 1.4 meters per second. So that's the speed of impact at the bottom when this red sphere gets to the bottom of its motion. And then there's this elastic collision. And in order to analyze an elastic collision, the method I went over in the notes, the lesson that I posted, and in the lesson videos is by taking advantage of the center of mass coordinate system. So the first thing we got to do is find the total momentum. So we're going to find E total is equal to m1v1 plus m2v2, and this is 0.1 kilograms times 1.4 meters per second plus 0 equals 0.14 kilogram meters per second. So that's the first step in finding the center of mass velocity. And that lets us now calculate the center of mass velocity, because the total momentum is also equal to the total mass times v center of mass. So that means v center of mass is equal to 0.14 over 0.3. Let's put units kilogram meters per second over 0.3 kilograms. So I took the total mass of these two objects. M1 is 0.1 kilograms and M2 is 0.2 kilograms. And it's the total mass that goes into this P equals mv formula with the center of mass velocity. So now is a weird part. We have to find each velocity relative to the center of mass. And the way we do this is a generic formula. V prime is equal to V minus V center of mass. The primed velocity um, the velocity with the apostrophe on it is indicating that that's the relative velocity. That's the velocity relative to the center of mass. And the way you find a relative velocity is you take an actual velocity, plane v, and subtract what you're doing it relative to. So, for example, v1 initial prime is v1 initial minus v center of mass. It might make sense for me to do these calculations. V1 initial is that, M2 is 0, V2 initial is 0, and P initial is equal to times that plus that times that. And then VCM is equal to the momentum divided by the total mass. So this was 0.467. Okay, so now I can actually do this calculation. V1 initial is 1.4 minus the center of mass velocity, which is 0.467. And that gives me the V1 initial prime. So I take the V1 initial minus the center of mass, 0.933. Prime equals 0.9. And we can do the same thing for V2. V2 initial prime is V2 initial minus V center of mass. We just take the regular velocity of the blue object before the collision. It wasn't moving, so that would be a 0 minus 0.467. And that gives us V2 initial prime is equal to negative 0.467. So now we have both velocities before the collision, that's the I is initial, relative to the center of mass, that's the prime mark. So now we're ready to go into step 4. In step 4, we have to do the collision. And in the collision, we have V final prime equal to minus, I'm going to put a variable here, epsilon times v final. And that epsilon is the elasticity. And if your collision is called elastic, then epsilon is equal to 1. So effectively, my v1 final prime is just minus v1 initial prime, which is minus 0.93. Done. I did the collision for object 1. Let's do the collision for object 2. v2 final prime equals minus v2 final initial prime equals plus 0.467. So all we have to do is take the initial velocity relative to the center of mass and reverse the direction. The initial velocity relative to the center of mass for object 1 was 0.933. We reverse the direction to negative 0.93. So now we have our step 5. We convert back to regular velocities. And take this formula that generated the v prime and just add v center of mass to both sides. Then you get v prime plus v center of mass is equal to plane v. So in order to use the primed velocity, we need to re-add the center of mass velocity. So we do it for object 1. v1 final is equal to v1 final prime plus v center of mass. So that is our negative 0.933 plus center of mass was 0.467. So v1 final is equal to that plus that is, as a coincidence, it's negative 0.467. It won't always be a familiar number like that. That's pure coincidence. And then I can do the same for v2. v2 final is v2 final prime plus v center of mass is 0.467 plus 0.467 is equal to 0.9. And this is actually fairly common if the initial velocity of an object was 0, then all we end up doing is subtracting the center of mass and then putting a minus so it turns into a plus center of mass velocity. And then we add the center of mass velocity again, and it turns out that the final velocity of object 2 is always twice the center of mass velocity if that object started from rest. So now we're done with the collision. And we just have to figure out how high these two things swing after the collision. Remember, the picture is that object 1 comes down, hits, and then they move away from each other and will achieve presumably different heights. So we can go with uh, the regular conservation of energy analysis, 1/2 mv squared equals mgh. This time the initial is the kinetic energy and the final is the potential energy. So the m's cancel and we do 1/2 of 0.467 squared equals h1, and let's cancel the m and divide the g under the other side. So that gives us h1 is equal to h1 is equal to 0.5 times that squared over 9.8. 0.011 meters. Do the same for object 2. 1/2 mv squared equals mgh. And for object 2, we have 1/2 times 0.33 squared over 9.8. H2 is equal to okay, we can actually do it. 0.044. Let's add another digit there. Is H2. And the first one will add another digit because I only had two significant figures there. So now we know the result. If M1, the 100 gram, is raised to 10 centimeters, then it will bounce back only 1 centimeter. M2 will rise up to 4.4 centimeters. We can find out if kinetic energy was conserved in the collision by examining the potential energy at the top of the swings. UGI equals M1, well, let's write it M1 G H1 initial. So that was 0.1 kilograms times 9.8 per kilogram times 10 centimeters is 0.1 meters is 0.098 joules. So if we have 0.098 joules after the collision, then we've conserved kinetic energy during the collision. So let's check U, G, 1, F is mass times G times 0.0111. Mass 1 times 9.8 times 0.011, 0.0109 joules. And then we can calculate the other one. UG2F is, it had a mass of 0.2, 0.8 and 0.04. So mass 2 times g is 9.8 times the height, and I get 0.0871 joules, and that gives me a total of U final. U final is equal to 0.0109 plus 0.0871 is equal to 0.098 joules. Check mark. I did conserve energy. The energy I had before the collision was the same as the energy I had after the collision. And instead of checking kinetic energy, we checked the potential energy instead because it was more accessible.